All right. Good morning, everybody. Our This is our last meeting for the semester in this class. Uh, so again, thanks to all of you, especially the people who have made it a regular part of your routine. It's helped me a lot get through the semester. Morning, Brooksy. Morning, Davis. Wait, I don't have my glasses. Sorry, I gotta go get my glasses. I can't see the screen at all. Morning, Vince. Okay, glasses. Morning, Dice K. All right, so anyway, this is our last meeting, and I really appreciate you guys who have been regular attendees. It helps a lot to know that someone's out there to talk to. Morning, Cappy. Uh, Morning, Ho Dave. Good morning, Dylan. So a bunch of you here today. Sorry I had to drink that down. It was close to spilling. Okay, so this is our last meeting. So a lot of you will just be done probably shortly after we get done meeting today, but I've got the schedule here, so let me just show you. The final lab, so some of you have submitted it, and I already reviewed those and posted scores, but you can turn in the final lab without a penalty uh, by this Friday, May 29th. That is the last day of the semester, so I don't accept any work of any kind after the last day of the semester. And then today's review lesson, which is due by this Friday as well. So remember, we've been doing Sundays since spring break, but this week, because Friday is the last day of the semester, this week's assignment is due by Friday. So anyway, please keep that in mind. And easiest, if most of you just keep doing what you've been doing, which is just to fill it out as we go, and then send it and be done. Okay, so let's just get that done, do a little bit of review, and I'll just, if there's any discussion to be done, I'll do it. So I'm going to go get the review questions. It's just like a homework. It's 10 questions, which to me are meant to be the major takeaway content of the course. I do think, I've said this before, I do think I am a better programmer for my exposure to assembly language programming. I don't think it's a significant part of my programming experience uh, in terms of solving new problems, but I do think that it's useful, and I do think that I am a better programmer for it. I certainly have taken advantage of my understanding of binary and hexadecimal to encode data in my applications. I use hexadecimal a lot, and I do use the bitwise operators a fair amount in my own programming. So I am a better programmer for it. But for a computer science student, I think it's mostly just about understanding that when you write a program in C++ or Java or Python or whatever it is, that ultimately what you are doing is you are giving instructions to a processor. So the assembly class is here to give you some sense of what the processor actually does and can do, and how it actually works. When you write a for loop, what does that look like for the processor? Okay, so let's do review questions. Hopefully I said good morning to everybody. Brooksy, Davis, Ho Dave, Vince, Cappy, Dice K, and Dylan. So I think I got all of you, but good morning again if I missed anybody. Okay, so we're going to do the Wikipedia style. For technical issues, I can almost always find the basic answers on Wikipedia, so that's part of what this lesson is about, is to make you feel empowered if you were in doubt, that it's okay to at least start with Wikipedia and then do deeper searching as required. So I'm going to bring up wikipedia.org, and let's just go hunt down answers for a while there. Until we find something that maybe we need to dig deeper. Okay, so instruction set architecture is first. pretty positive that they have. Fortunately, when it comes to technical questions, there's not really anybody's personal politics that's gonna um, color the their content. So um, it, being a liberal or conservative or whatever obviously doesn't matter when it comes to describing something of a technical nature. So I don't hesitate to use Wikipedia and sort of trust that it's usually um, fairly accurate. Okay, so instruction set architecture. Um, uh, what's our question? Define instruction set architecture, emphasizing those aspects of an ISA most relevant to programmers. All right, so let's go get the definition, which is just this first sentence. So an instruction set architecture is an abstract model of a computer. It is also referred to, let's grab the second sentence too. I like that. I don't think we need the third part, but the first two sentences are good for defining what do we mean by instruction set architecture. Abstract model of a computer, also referred to as an architecture or a computer architecture. So I'm going to grab those things and plug them into my answer. And then I'm going to space down and get the programmer part. Okay, so it should be the second paragraph that's the programmer part. So in general, an instruction set architecture defines the supported data types, which is important to programmers. The registers, which is where you store, load, manipulate data, so that's important to programmers. The hardware support for managing main memory fundamental features. Addressing modes as an example, so if we put data in memory, how do we access it? So also important to programmers. And the input-output model. So all of that stuff, and that's really what we've done in projects since like project 4 or 5 is all of that stuff. So the stuff that's important to people who want to make applications using a processor is all that second paragraph right there. So I'm grabbing the whole thing. By the way, a lot of these things are the same kinds of questions you ask about high-level languages like C++. So what are the data types? How do you make variables? How do you access memory? In C++, for example, we have pass by value, pass by reference. We have pointers. C++ sort of has the full complement of how do you address memory. And even though it's slightly different in its meaning, we also usually want to know how do you do inputs and outputs in a high-level language. So it turns out that the same sort of major issues for programming a processor are the same ones for programming in a high-level language. Okay, so there's my first answer. I'm going to go back to Wikipedia and do a new search. The next one is CPU, which I bet I can just search by CPU. Yeah, it brings me straight to Central Processing Unit. What's the question? Define Central Processing Unit. This is a pretty softball question, isn't it? Central Processing Unit, also called a central processor, is the electronic circuitry within a computer that executes instructions that make up a computer program. So that's good. I also like the second sentence here. The CPU performs basic arithmetic, logic, control, and I/O operations specified by the instructions in the program. So I like the first two sentences to define what is a CPU. The second sentence gives you the additional detail. That's nice. So fundamentally, it's just an electronic circuit that executes instructions, but it's useful to have the extra detail that when we say instructions, what kinds of things are we talking about? Math, logic, which would be comparing things. We didn't really do any kind of control stuff, but I guess you could say we wrote software to control circuits. And I/O. Okay, so there's the second one. This is going to go fast. Hopefully I'm not going too fast. You can always just ask me to hit pause if you want, but probably you're just doing what I'm doing, which is just grabbing the words that answer the question well. Number 3, system on a chip. So I'm betting that I can just put SOC in Wikipedia. Okay, I'm going to have to look. So it's way down here, system on a chip. That's the one that we want. In fact, the picture in the little pop-up there is not that dissimilar from what we've been using. Okay, so the question is define system on a chip. System on a chip is an integrated circuit that integrates all or most components of a computer or other electronic system. And again, sort of reading beyond that to get the extra details makes for a better answer. So when we say components, what do we mean? The CPU, memory, I/O ports, and some kind of secondary storage, all in a single substrate or microchip. The size of a coin thing. Yeah, I guess that's okay. I don't think we need any more beyond that. So I like these first 2 sentences for this answer. The size of a coin bit I find a little off-putting, but I can live with it. I'm going to clean this up, so you guys should do the same thing. Like all this, get that crap out of there. We don't need all that. How do you pronounce this stuff? A system on a chip, or SoC, is an integrated circuit, also known as a chip, that integrates all or most components of a computer or other electronic system. And to remind you on our board, so the Nucleo board is not the system on a chip. The system on a chip is actually the processor. I'm not going to worry about it, but if you look in the middle of your board, there's the big square quad flat package. That's the system on a chip. The Nucleo board has added I/O connections around it. Maybe I should put my camera up. I'm putting my camera up. I feel guilty. All right, this still have stuff wired to it, but the system on a chip for our board, so the Nucleo board is really about adding input-output connections. The system on a chip, and you probably already knew this, that's this right here. That's the whole system on a chip, is that little square chip right there. So it has memory in it, it has the I/O connectors, it has the processor in it, it has the floating point optional unit on the processor in it. That's the system on a chip, that thing right there. Oh, and I'm doing that and you can't even see it. So I will redo that part. The system on a chip is this square right here, right? This board around it is really just making it easier to do inputs and outputs. But the board, all of its components are actually wired to the system on a chip, which is what the little leads coming off the square. So that's the thing that's the size of a coin that has the processor, the memory, the input-output wiring. That's the system on a chip. And then the board around it, the Nucleo board, really is just making it easier for people to build circuits to those connections. Let me pretty up my desktop a little. So, system on a chip. That thing right there. I probably don't need that picture anymore, but I'll leave it. And it is about the size of a coin. Okay, number 4. ARM, the architecture, and then ARM, the company. So let's go to Wikipedia, and I'm going to try ARM. Let's try ARM CPU. That's a lot easier to type than ARM, the architecture. So the first result I get is ARM architecture, so that's terrific, because that's what I want. ARM architecture. So probably you've noticed all of our answers so far come straight off of Wikipedia, and I've pretty much liked the words that they've chosen to use, so I'm happy with it. All right, so the question again is, what is ARM, the architecture? So ARM, previously Advanced RISC Machine, originally Acorn RISC Machine, is a family of reduced instruction set computing architectures for computer processors configured for various environments. The next sentence talks about ARM holdings. So in this case, we just need this first sentence here. This is what ARM, the architecture, is. It's a family of reduced instruction set computers. That's it. And the reason why this question is here, of course, is because in our class, I chose to use the ARM architecture, the Cortex M4 specifically, for our experience with computer organization and architecture. There were other architectures I could have chosen, like Intel, but I chose this one. It's a very popular one right now. Okay, there's ARM. The architecture, ARM, the company is the next thing down, which I could go to the ARM holdings page, but I think that this next sentence might actually answer the question for me. So what is ARM, the company? ARM Holdings, ARM, the company, develops the architecture and licenses it to other companies who design their own products that implement one of those architectures. I like all of that stuff. It's a long answer, but I like all of it. The whole rest of that paragraph starting at ARM Holdings, I think that has good detail about what the company does. So I'm going to grab all of the rest of that for what is ARM, the company. I might break it up into two pieces. Yeah. So I think this would read better if I say holdings. So I'm just making this sort of read like I bothered myself to want it to read nicely. So most of you probably remember this, but ARM, the company, they don't actually make processors, they design architectures. So there's a difference between designing an architecture and making the actual hardware processor. And ARM only does the designing the architecture part. And then they sell the designs to companies who make chips. That's mostly it. In fact, that's not mostly it, that's it. Okay, so hopefully everyone's doing okay. I'm sort of just delaying a little bit here. But you saw where I got the answers. Okay, reduced instruction set computer. So why is this question here? Because there's a reference to reduced instruction set computers in question 4. Reduced instruction set computer. So it seems useful to ask and have it explained. What is that exactly? So we're going to go look that up next. I'm going to search it. So I'm going to search RISC. All right, so on this page, just be careful because there's other sort of RISC-oriented issues. We want reduced instruction set computer, so I'm going to follow this first link here. Reduced instruction set computer. So that's the kinds of architectures that ARM Holdings, the company, designs and licenses to people. So what does that mean when we say that? So reduced instruction set computer is a computer instruction set that allows a computer's microprocessor to have fewer cycles per instruction than a complex instruction set computer. And then I think that there's good additional detail down here in the second paragraph. So the main,
has a small set of simple and general instructions rather than a large set of complex and specialized ones. The main distinguishing feature of RISC is that the instruction set is optimized for a highly regular instruction pipeline flow. I don't know that that really helps us. Although it does then the next sentence talk about load store, in which memory is accessed through specific instructions rather than as a part of most instructions. So I like all of that, the first two paragraphs. And I'm going to clean them up because there's some like footnotey bits and stuff. But I like all of that. And then I'm going to go clean it up so it doesn't look like slop. I don't think we need the help in pronouncing RISC. I don't need this footnote. So reduced instruction set computer, or RISC, is a computer instruction set. So the idea here, of course, is that this is one way to design a processor architecture, and then people make the actual hardware CPU based on those designs. So what you end up with ultimately is a CPU, like our Cortex-M, the actual piece of hardware that in it has this reduced instruction set. What's key about it is that this design, the reduced instruction set, means that a computer's processor uses fewer cycles per instruction than the other major kind of processor, which is the complex instruction set computer. The best example of a CISC, or complex instruction set computer, is Intel. Theirs is a complex instruction set computer, which means that they have a lot more instructions. That usually means, by the way, that it's easier to write more complicated algorithms on a CISC machine, whereas on a RISC machine you have to write more instructions because there's not very many specialized instructions. But in general they use less power and the circuitry is simpler to build. Okay, has a small set of simple, I'm looking through this to clean it up rather than a large set of complex and specialized ones. The main distinguishing feature of RISC is that the instruction set is optimized for a highly regular. This second sentence doesn't really help us that much because we haven't talked about pipelines. But let's just leave it. Doesn't hurt anybody. We are familiar with the fact that they use load store. What we mean by that is that to access data in memory, you have to go through a series of steps to load an address, load a value, manipulate a value, and then store it back into memory. On a complex instruction set computer, there are instructions that kind of just magically fetch and store the data back for you, but not on a RISC machine. Okay, check and chat. So anyway, I took the first two paragraphs and I cleaned them up and I separated them out so that they look pretty. Okay, so you notice though the nature of the questions is just to keep following a thread of thinking. So ARM is RISC. What is RISC? And then there's a reference to load store, so let's go get a definition of that. I'm betting, if I go back to Wikipedia, yeah, so if you notice right here is a link to load store. So I'm going to follow it. Right here in the second paragraph, by footnote number 3, there's a link to another Wikipedia entry. So let's go grab that. All right, so what is load store? In computer engineering, a load store architecture is an instruction set architecture, ISA, which connects us back to the first question, that divides instructions into two categories: memory access and ALU operations. We're going to clean that up a little bit so that it reads good, but I'm going to go grab that. Whole first sentence is pretty good for this answer with a little bit of help. And hopefully you can put all the pieces together. So ARM is an instruction set architecture. Specifically, it's a reduced instruction set architecture. And it is, as is common for reduced instruction set computers, it is a load store architecture. All that means is that you have the instructions to load and store data to and from memory are separated from the instructions that do arithmetic and logic. That's all that means. Right here where it says ALU, I think it would be nice to spell that out, which they didn't on the Wikipedia page, and they should have. So the two categories of instructions in the load store architecture are memory access instructions, which we know as LDR and STR. There are others, but those are the ones that we've used. And the arithmetic logic unit operations, which would be add, subtract, divide, multiply, compare, the if-then block instructions, all of that stuff is logic. And then it points out that in a load store architecture, you have to get data into registers to work on it, which we are aware of. You can't just work on variables in memory directly. You have to load an address, load a value, work on the value, and then store the value back. And we know that from our own experience. Okay, that's number 7. But hopefully you're seeing how these things are all connected to the processor that we explored in this class. All right, now we get down into our own memories. Actually, I'll let chat do this part, if you don't mind. So I'm going to write out the blanks, set a bit, clear a bit, toggle a bit, test a bit, and then I'll let chat give me those. So it'll give you a chance to sort of get back involved directly. So what's the first one? What did I do? Set a bit. So, okay, outstanding. We use OR to set a bit. That's the same always, by the way. That bitwise operation, whatever it looks like, that's what it is used for in programming, is to set a bit, make it be 1 as opposed to 0. And you have bitwise logic operators in all of the high-level languages, so you can actually use this trick. The second one is clear a bit. Yep, or perfect. The second one, clear a bit. Bic, that's true. Yep, outstanding. Bic, toggle. EOR. Perfect. Exclusive OR. So just these are just sort of to leave these thoughts in your head, because you can use these tricks in high-level languages. If you go exploring how do you do bitwise logic, then you'll find that you can use some of these operations if you're clever in high-level programming as well. And then the last is to test a bit. Yep, that's the ARM one. You can also use the AND instruction as a way of testing. On the ARM processor, it's way easier to just use the TST, the test instruction, but you can also use an AND instruction as a way of getting at testing to see if a bit is set. So test is good, but I'll remind you for your later programming life that the AND instruction or bitwise operation can also be used as a way of testing to see if a bit is set. All right, so we're pretty happy there. And then we just do a couple of, just to sort of leave you with, so how do we write? There's actually two ways to write an if statement. It's probably awkward for you to do it in chat. You can if you want. But probably you know what I'm about to do. So add 1 to R if the value is less than 10. So this does depend on whether or not it's signed or unsigned, but typically how you would implement in ARM this operation is you compare R0 with 10. And then you use an if-then block saying if R0 is lower than LO 10, and then add if it was lower than, add 1 to R1. So we're testing R0, but incrementing R1. So that's the sort of pure ARM way to do it. You can also do this without an IT block in ARM. So without an RT block in ARM, you would do this. You'd still do the comparison. And then we would do well, we want to do branch if it's greater than or equal to. So what is that going to be higher than? I'm going to have to go look. We're going to go look at the ARM condition flags. Because what we want is unsigned greater than or equal to. Which there should be. Okay, here it is. This little table here. Unsigned greater than or equal to. There's signed greater than or equal to. We don't want that. We want unsigned greater than or equal to. Right here. Unsigned higher or same. Okay, so now we know how to write that. Branch if higher than the same. To a label that I will call do not increment. There's the label. So this is the non-IT block way of doing that same logic, where we use a branch and a label to skip over the code we don't want to execute in certain circumstances. But if I'm on ARM, I'm using the if-then block style because it's just so elegant. It's just such a nice way to do it, as opposed to these sort of awkward branching and label statements, and you kind of end up getting a mess when you do that. But I just wanted to show you that there is a way to do it without the if-then block by using, you still use the compare, but then you use branching and labels to sort of get around what you don't want to happen. Okay, that brings us to the last one. Hopefully I'm not trying your patience. I want to give you your money's worth. One of the reasons, well, by the way, on number 9, why I wrote it that way is because that looks very, very similar to the way it would be written on Intel architecture. The difference on Intel would be that they use instead of calling it branching, they call it jumping in Intel. So you would see jump instructions. But you'd still see comparisons, you'd still see labels, but they call it jumping in Intel as opposed to branching. It's probably because ARM is English people, and that sounds sort of European-y to me, whereas jumping sounds like something an American might say. But I don't know why the difference in the semantics. But anyway, in Intel, it would be jump something. Okay. Last one. This is it. An ARM. Okay, so this NOP right here, that stands for no op. I'll put a note. NOP is no operation or no op. I'll go look it up just to show you. It's not super important, but let me go to Wikipedia and just show you what no op is. I bet that they have no op. Yeah. So on Wikipedia, so what do we mean by no op? It's an assembly language instruction that does nothing. So it literally just tells the processor to waste a cycle. The processor will just sit there and do nothing for a cycle. You don't really typically need that as a programmer, but if you ever get exposed to pipelining, you're going to see no ops. So no ops are a trick used by people to optimize the performance of a processor. For our purposes, we don't really need a no op, but anyway, that's what we're doing is we're writing a no op loop, and that's mostly just to practice writing a loop, right? But anyway, that's, if you wanted to know, that is an instruction, and what it tells the processor to do is nothing. And usually that's done to achieve timing effects for the purposes of making some operations run more efficiently. It seems like it wouldn't, but that's how it's used sometimes. Okay, so we just need to write a loop that does a no op 10 times. So to do that, we're going to need a counter. So I'll just use R0. You could start it at 0, but I'm just going to count from 1 to 10. You've seen this loop before. So there's my for I equals 0. Here's a label to mark the part where I can jump back to. We're going to execute a no op. We're going to increment our counter. And then we will see if our counter has reached 10. What was that about? I'm just spreading these out so that you can read it better. So there's the no op that the loop does, which is just kind of wasting the processor's time. Here's incrementing my counter by 1, and then I'm going to see if I've reached 10. And I'm going to use an if-then block because that's just so nice to write in ARM assembly. If I'm still lower than 10, then I can branch when I'm lower than 10 back to the top of the for loop. It turns out that in assembly, loops, they end up kind of feeling pretty similar to the way you write them in a high-level language anyway, except for they're less compact, right? So it's nice to write for int I equals 0, I less than 10, I plus plus, to achieve the same effect. So there is the loop. I'm going to save my work. This is I guess I'll call it a homework. Yeah. Okay, so that's the whole show. And those last two are there. The part of the experience is just so you kind of have a sense in your head when what am I making the processor do when I write an if statement or when I write a for loop. Which I guess is kind of like if you were a race car driver and they asked you to take a course on internal combustion engines and transmissions would be kind of a similar thing, like what's going on under the hood, which some people would believe would make you a better driver, or in our case, a better computer scientist. And for some of you, you may end up experiencing in your careers something that involves assembly language. You may end up helping to create a new programming language, in which case you would need to know how assembly works. There may be some of you who end up working on systems where you do write the assembly language, or you write something like the C language with assembly embedded inside of it. So in those cases, it could be helpful, sort of like directly helpful as well. Okay, I think otherwise that is it. You guys are done with me. So don't forget, the drop dead date is Friday, so I'm going to wake up on Saturday morning, which is after they're paying me anymore, and I'm going to knock out all my grading and start my summer as soon as possible. So if you want anything graded, it needs to get to me before I wake up on Saturday morning, which would be May 30th, meaning please send it by May 29th. I will be doing my normal office hour broadcast tomorrow morning at 10 a.m. So if you have lingering questions tomorrow at 10 a.m., please show up for that, and I'll answer your questions. Otherwise, I appreciate the hard work that you've done. Yeah, so there's a question about am I doing... Yeah, so our department is entirely online in the fall. So I'm doing the basic Linux operators class. I'm doing 2 sections of programming and algorithms 2, and I'm doing this class, all 4 of those online in the fall. This class, for those of you, you're probably the last class in my career that gets to actually get your hands on hardware. So I think it would be very difficult to get through this class if we didn't have any time together to sort of get your software set up on your own computers and to sort of get you comfortable with the hardware. So they're going to do Intel assembly, and they won't get to look at or touch any hardware basically in the fall. But yeah, the whole computer science, everything will be online again in the fall. Thanks, Brooksy. I appreciate it, man. I appreciate all of you who are, again, regular attendees, my live audience, which is small but reliable, and I really, really appreciate it. It's made a huge difference to my existence doing this, because this is not what I would choose to do. Yeah, Davis, so in an hour we'll do our last thing in programming algorithms 2 as well. Thanks, Cappy, I appreciate it. Yeah, it was a pain, but now we're through, so feels good to put one to bed. Thanks, David, I appreciate it. All right, again, so if anyone has any questions, I will be here at 10 a.m. tomorrow, but otherwise we're done, so email me. Thanks, Vince. Good luck, everybody, whatever it is that comes next for you. If it ever crosses your mind, by the way, I'd like to hear what people are getting up to, so if something neat happens for you, I'm always sort of eager to hear about that, because that's why I do this job, is so that hopefully you go out and do something neat in your life someday. Thanks, Dice K. Appreciate it. See you, Jack. So everybody, have a good summer, whatever it is that comes next for you. Email me if you have questions, and otherwise, take care, and thanks for all the hard work that you did this semester. Thanks, Dylan. Appreciate it.